my ideal and perfect boundary conditions. Okay? So how do I do this? Here's my sample. And basically, I have controlled heat sinks at both ends made of a material that is in good contact with the sample. So I put the two heat sinks, a hot one in red, a cold one on the other side, and I guarantee that that material basically has an almost perfect contact that makes sure that the real temperature at this end is T1 and the temperature at this end is T2. So then I heat up this one in a controlled manner with a feedback loop that guarantees that the temperature of this side remains always at T1. Then I cool the other one with, again, a feedback loop in such a way that I guarantee that the temperature of the other one remains always at T2. Now once that's done, then I can create my steady state condition by which T1 is here, T2 is here, straight line here. The slope of the straight line is the K I'm looking for. Okay? So basically, my heat flux now is described by this simple equation, straight line, T1 minus T2 divided by L, which is the thickness, and then I have basically the heat flux to the problem. I have solved my problem. Okay? So by doing an experiment with the material, whatever I have in the middle, I can actually guarantee that now I have K, and with that K, I can actually solve the problem. So the QIs that I'm introducing at both ends, in and out, have to be the same, and they're related to the heat flux by the area. So if I divide the total heat input and the total heat output by the area, I get the heat flux I'm looking for. So in a way, that is a very simple standard. I just define the problem, I define how to solve the problem, how to find the variables that I'm looking for, and how to use that variable to model the heat transfer to the wall. Okay? But I have errors, and the errors are of several forms. Now, there's intrinsic errors that are associated to the measurements and procedures. You know, the not perfect contact resistance, the quality of my thermocouple, how well I can control, for example, the heat fluxes. But I can assess those, and I can evaluate them until I get a sense of my error bars associated to the measurements themselves. So, in general, they can be quantified and assessed. And there's the problems that are intrinsic to the assumptions. So I made assumptions, one-dimensional, steady state, and many others. Okay, and I have to understand if the problems that come intrinsic to the assumptions are actually problems that are going to represent an issue for my standard. So, for example, I can have issues like surface condensation and evaporation. In houses, there's humidity, and generally there is a film of water that forms in the colder surfaces. So I might have to introduce this into the problem. But I have to look at it in a careful way, because is it a problem of the thermal conductivity of the material, of the wall itself, or not? Or is it a problem of the environment? So is it a problem of my model that I need to introduce that? Or it is a problem of the way I assess the heat transfer through the wall? Now, in this particular case, most likely the problem is not a function of the material property. It has nothing to do with K. It's basically with the way I model the environment. So I would have to put a correction to my Q, but it has nothing to do with what the standard was assessing. So the question of heat transfer, that is a problem. Temperatures change during the day, so there might be a transient, and that transient might need a further analysis, and that further analysis is associated to other parameters that I have to evaluate in a different way. But in that case, I will have to create another test that enables me to get ρ and Cp, which are the other parameters that allow me to look into the transient part. Now, the one-dimensional assumption, well, I have to look into the corners, assess it, and all that stuff. But again, it's only a problem if the thermal conductivity is a function of the dimensions. So if the thermal conductivity is the same in all directions, then it doesn't affect my test. So as you can see, I have created a simple test for a simple problem, and a standard is actually very useful, and a list of very well-defined problems that I need to address before I actually use the standard in an effective manner. So this is in a way what I believe is a proper mechanism to develop a standard. Obviously, it's oversimplified, and obviously I have not covered everything, but I think in a way it gives an example of how to put a standard together. Now, how do we do this to fire? And this is where the problem starts. First of all, we have to establish the relevant properties. What is the K for fire? And there's a multiplicity of them. You know, the relevant properties need to be separated from environmental variables, and that's a very difficult process because fire affects many of these properties in a sort of feedback loop type of situation. So it's a little bit of a complicated situation. The standard has to be able to assess these properties and establish estimates of error, And I think in fire we have not been very good at actually doing this part of the problem. So I'm going to take an example of a fire standard to walk you through an attempt to make a good standard for fire. I just use this as an example. There's many others, but this is a real serious attempt of creating a good standard. And this is this ASTM 1321, which is the lift apparatus. So I'm just going to take one of the tests, the ignition test. You put the sample, you heat it up with a radar panel, you have a large pilot flame here, and you wait until ignition occurs. And on the basis of that principle, you actually come up with some answers. It's the simplest possible case, very similar to the one that I treated with the wall. It's a one-dimensional heat input on this direction. You insulate the back, so you neglect the back. And basically, it's a one-dimensional problem with a constant external heat flux and an insulated back. So we simplify the problem to its minimum expression. Now, we create a laminar boundary layer, which is extremely important because a laminar boundary layer is going to carry all the fuel into the pilot. So it's going to make a very robust ignition mechanism. For example, the cone calorimeter is much less robust because it's horizontal. So the positioning of your pilot in the cone calorimeter is critical because the plume is unstable. It's a fluid mechanic problem that is very difficult to describe. So where you place the pilot becomes a critical point in the analysis. In here, this was designed in a very careful manner in such a way that you had a massive pilot that would basically affect the entire collection of fuel that was being produced by the sample. Okay? So in a way, this is a properly defined boundary condition for this particular problem. The truth is that that is the definition of the standard, but this is the reality of the ignition problem. Now, you might wonder what all these little things are here, but these are all the things that are happening. You know, from the production of fuel, the diffusion of oxygen, distributions of oxygen concentration in depth, you know, the distribution of fuel on top. You have convective boundary conditions, you have surface irradiation, you have all these other things, even heat losses to the back. And this real problem, even if I keep it one-dimensional with a constant heat flux, is a much more complicated problem than the one that the standard described. So, if I want to describe the proper problem, then I have a much more complicated differential equation with much more complicated boundary conditions. Now, at the end of the day, I want to know how much fuel is coming out, and this is a function of a lot of different variables, and not a single variable that like I had before, which was K. So now I have a compounded set of variables that I really need to incorporate into my standard. So what the standard did was basically simplify the problem completely, and basically ignored most of what was happening, and basically said that, you know, what really is happening in this case is that you're heating the material, and the material is heating up, temperature at the surface is higher than at the back, and it increases until it reaches a pyrolysis temperature. Then you start producing fuel, and then eventually the fuel creates a flammable mixture, and the pilot creates the first flash, and that's what we call the flash point. Eventually, once you produce enough fuel, you have enough fuel to sustain a flame over the surface, and that becomes the fire point, and this is the second element. That is what at the end we consider as ignition. The flow is an important parameter, but we fix the flow so we can standardize the conditions of the test, and the piloted ignition minimizes all other environmental variables because it puts a huge heat source here that as soon as you get into this flammable regime, it will ignite everything. But what does the standard do? The standard basically eliminates all this and just simply says the time to get to pyrolysis is much, much longer than everything else. Okay? So I can ignore flash point, I can ignore fire point, and call the ignition the point where you start producing flammable gases. Okay? By doing that, then all your equation becomes inert. You don't have any of the heat sources, the heat sinks, all these complicated elements, and you're saying basically I am heating an inert solid. And this is exactly like the heat transfer problem that I touched at the beginning. So you've completely simplified the whole physics of the problem and just brought it back to its simplest common denominator.